Welcome, product managers. Today, we're diving into this explainer to unpack the complete theory of computer vision. We're going to look way past all the buzzwords and hype to give you the exact framework you need to build smarter, vastly more capable products. We're covering the whole shebang, from the foundational theory straight through to the hard metrics and down to the real-world guardrails you actually need to deploy this tech in the wild. Let's get to it. But before we jump right into the technical weeds, I want you to ask yourself a foundational question about the future of your roadmap. Can you build a product that actually sees? I mean, really think about that for a second. For decades, our software has basically been completely blind, right? It relies entirely on manual user inputs, clicks, keystrokes, taps. But what if your product could interpret the visual world around it just as effortlessly as a human operator?
Well, computer vision is exactly the technology making that possible. It's this highly specialized, frankly amazing field of AI that allows our systems to pull actual, actionable meaning from digital images, video frames, and live camera streams. So instead of just sitting there storing a flat JPEG on a server, your system actually understands what's inside that image. It's literally turning raw pixels into actionable business insights and massive, scalable automation. Okay, here's a quick look at the roadmap for this explainer. We're going to walk through the foundation, look at core capabilities, dive into the PM metrics matrix, map out the CV development roadmap, and finally touch on ethics, bias, and privacy.
So, let's kick these off at Section 1, the foundation. Let's figure out how this specific AI discipline actually fits into your overall tech stack. You know, trying to reproduce the sheer efficiency of human biological vision is a monumental technical challenge. We do it effortlessly. We just take in our surroundings without a second thought. But teaching a machine to do that requires a total shift in how we build software. Computer vision leans heavily on deep learning. Instead of an engineer sitting down and trying to explicitly write thousands of if-then rules for what a cat or a car looks like, which is basically impossible when you think about all the natural variations, the machine uses neural networks to essentially teach itself. It learns hierarchical representations, identifying complex visual patterns across millions of training images, and figures out the variables completely on its own.
All right, moving right along to Section 2, core capabilities. Let's talk about what computer vision can actually do for your users.
One of the absolute foundational capabilities here is object detection. This is where a machine literally draws mathematical boundaries, those little bounding boxes you've probably seen, around everyday items. It does this to understand both what they are and where they are. So it's not just broadly classifying a scene as, say, an office. No, it's pinpointing the exact pixel coordinates of a laptop, a vase, a bottle, a mouse, a bowl, or a cup. This core capability is the absolute backbone for countless product features. Whether you're monitoring retail inventory on a super crowded shelf or building autonomous vehicles needing to track pedestrians in real time. To really anchor this theory in reality, just consider Amazon Go stores. Their automated checkout completely relies on semantic segmentation, which is a technique that categorizes every single pixel in a frame, combined with object tracking. By fusing computer vision with physical sensors, the system is tracking customers and items simultaneously. A shopper grabs a sandwich, the system watches, understands the interaction, and just seamlessly updates a virtual cart. Boom, no checkout lines. The product simply observes the physical world and automates the entire transaction. It's a real game changer.
We're also seeing a massive, life-saving impact in healthcare, where computer vision acts as this unblinking, highly accurate extra pair of eyes for physicians. It's known as computer-aided diagnosis. These systems analyze multidimensional medical imaging, like complex MRIs or X-rays, and they are meticulously trained to spot incredibly subtle abnormalities. We're talking about things like tiny retinal lesions for diabetic retinopathy, or early-stage tumors in brain scans that could so easily escape human detection entirely.
But how do we actually know if these features are working out in the wild? Well, that brings us to Section 3, the PM metrics matrix.
As a product manager, you're sitting right at the center of 4 distinct and honestly often totally conflicting layers of metrics. You've got your data scientists, and they are understandably obsessed with model metrics, like accuracy. Then your engineers are laser-focused on system metrics like latency and throughput or frames per second. Meanwhile, you own the product metrics. Did the user actually succeed in their task? How long did it take? And of course, your stakeholders are tapping their watches, looking at business metrics, demanding proof that this multi-million-dollar AI investment actually drove ROI or massive cost savings. I'll tell you right now, Optimizing just one of these layers while completely ignoring the others is a guaranteed way to break your product.
Let's drill down a bit into those model metrics, because knowing when to prioritize precision over recall, or vice versa, is absolutely crucial. Now, accuracy is just the overall percentage of correct predictions, but honestly, looking only at accuracy can be dangerously misleading. Precision asks a different question. Out of everything we flagged, how much was actually correct? You need super high precision for something like a spam filter, because deleting a real important email is completely unacceptable. Recall, on the flip side, asks, out of all the positive items out there, what percentage did we actually catch? You want high recall for fraud detection, because missing a single fraudulent transaction is catastrophic. In that case, you'd much rather investigate a few false alarms to make sure you catch everything.
And this right here leads to the ultimate product trade-off tension. Imagine you have a highly accurate, mathematically perfect model, but it takes 30 seconds to load a result. If it's that slow, your users are going to abandon the feature long before it finishes, making that perfect precision completely useless. As the PM, you have to make the tough call. Sometimes a slightly less accurate model that gives you an answer in 1 second is significantly better for overall task success than a flawless model that just leaves your users staring at a spinning wheel of death.
Okay, so how do we actually go about building this? Let's move over to Section 4, the CV Development Roadmap.
Your execution blueprint generally follows 3 essential steps. First up is data collection and annotation. Your model is literally only as good as the data you feed it, which usually means auditing and gathering high-quality visual data and having humans spend hundreds or even thousands of hours manually labeling it. Next, we hit model training and testing. This is where you use neural networks to learn the patterns and fiercely validate them against real-world test scenarios. And finally, continuous optimization. The work definitely isn't over just because you launched. AI models experience drift, so you have to continuously train them on fresh data to adapt to changing user environments over time.
Look, before your engineers write a single line of code, you really need to run your feature through this PM decision framework. Ask yourself, what exactly is the core visual task? Are you classifying an image, detecting objects, or reading text via OCR? Second, can human annotators even reliably label the required data for your specific use case? Third, what is the actual business cost if you get a false positive or negative? And crucially, will the system function reliably in diverse lighting and real-world environments? If your user tries to use your app in a dim room, is the whole thing going to break? You need to know that up front.
Finally, we reach our last and honestly, arguably our most important section: ethics, bias, and privacy. Whenever you're building products that literally look at the physical world, you are interacting directly with real people, so the stakes get extremely high very quickly. If the data you train your model on is skewed, well, your AI is just going to scale up those exact same human blind spots. That's algorithmic bias. There's also a massive, very real conversation happening right now around the loss of individual privacy, unauthorized access to biometric data, and mass surveillance in public spaces. Oh, and let's not forget false positives that lead to totally unfair real-world consequences. These aren't just academic concerns, folks. They are practical, rigorous design constraints you have to navigate.
The real-world impact here is no joke. As our slide highlights, the ramifications of biased data include false accusations from facial recognition systems, healthcare diagnostics that don't consider the situations of specific cohorts of patients, or financial loan decisions that misalign certain members of communities. When facial recognition tech struggles across different demographics, it can ruin lives. Making sure your training data is equitable isn't just some nice-to-have afterthought. It is absolutely just as vital to your job as hitting your latency or your revenue metrics.
So as you go out there to build the next generation of visual products, I want to leave you with one final, provocative question to chew on. Will your product's vision be fair to everyone? Computer vision gives us this unprecedented, almost unbelievable ability to automate, analyze, and innovate at scale. But at the end of the day, it is entirely up to us to deploy this power thoughtfully. Thanks so much for joining me for this explainer. Now get out there and build something incredible.